Welcome to all. We are starting the real important part of structural engineering. I already uploaded some classes earlier where I told the importance of this one, and one more I uploaded just now where I told two important things. One, I will be very slow. Very means not dragging, quite slow, so that everybody will understand. If someone feels it is very slow, you can change the speed. This I told there. 1.25 is there, 1.5 is there. But still I feel if you are really learning from me, go at the normal speed. Second point I told just now. Just now means the previous uploaded part. When I write, see, today I am written so many things here. But as we go further, so many things are there which if I keep on writing on the board will take a lot of time. Therefore, I told I will dictate. Those who want should note down or pause the class and write and continue. Or I told one more option for you that I don't want to talk here. See the previous class uploaded, which is not the regular class, information class. I wrote heading one more information. Okay, start. Types of loads. In structural engineering, all the structural members are subjected to some loads. And remember, slowly later I will tell, loads are not resisted by structural members. It's a wrong concept. You cannot tell a beam is required to resist a load. No, it will receive the load and transfer to some supporting member. So loads are received and transferred. Then, but due to this application of the load somewhere along the member length and transferring it to some other member, the cross section of member is subjected to section forces, namely axial force, shear force, bending moment or twisting moment. They cannot be transferred, they should be resisted. This all comes in strength of materials. So important is loads are applied on the structural members which subsequently are transferred to supporting members. But our important is what are the different types of loads which you come across in structural engineering. See, I written here, you should write, there are two types of load mainly. One, concentrated load or point load. Usually, concentrated load to pronounce will take more time. Sometime I will tell concentrated load. Okay, people understand. But still simple is point load. That is load acting at a point. It is represented by an arrow mark. See here, say W. Here, concentrated load is directly defined by magnitude of load, say W. Further, I will tell later. Once my first round is over, this is introduction. Second round is separately point load, separately distributed load, there separately UDL, separately this UVL, that UVL and this UVL. Therefore, right now I am giving introduction. So understand that way. It is acting at a point represented by an arrow mark. Now come to, further I will not tell because actually majority of people are knowing point load. Still, subject point of view. So this over now, load acting at a point represented by an arrow mark that defined by magnitude, that is W, say. Distributed load. That is, load is distributed over some length. It is distributed or spread, you can tell. Either distributed or spread. Along over some length. The length along the member over which load is distributed or spread is called loaded length. Say, some symbol I will put here, loaded length, say L0. I will tell you why I use L naught. Sometimes a simply supported beam is of span L, loaded by UDL, just for understanding. Total load equal to, some will tell, total load is always equal to intensity into span. If you practice that way, by chance, see, I write here, use the space. There is a simply supported beam or any beam. This all will come later. If the load is fully distributed, okay, loaded, see, if the span is L, loaded length is L, sometimes people will tell total load equal to intensity of load into span. Correct. But if the same beam of span L is loaded by either UDL or UVL, anything, load is spread only for a length of L naught, some length. Now, those people who practice by somewhat what you call is by hearting procedure or mechanically practice, what they will tell, total load equal to W into L. No, it is W into L naught. So that's why I never tell L as the loaded length. L I always use for length of member. So I will tell loaded length is L naught. So remove it. That's the reason why I told L naught. L naught can be equal to L. Okay. Load is distributed or spread over some length. The length along the member over which load is distributed or spread is called loaded length. I used red color for important terms. Loaded length, say L naught. Distributed load is defined by intensity of load. See, point load or concentrated load is defined directly by magnitude. I will give example little later now. But distributed load is defined by intensity of load. Intensity means load per unit length. Load per unit length. Remember, it is not a total load. Load per unit length. Little later, I will give example for you. Now, also, see, point load is represented by just an arrow mark. Distributed load is represented by a diagram. You require a diagram. Next. That is the diagram representing the load. Now, where loaded length is along the member. See, loaded length is along the member. And intensity is perpendicular to member. This all I will explain. Suppose a member is loaded by distributed load. Along the length, you mark loaded length. Some geometric figure will come, rectangle or triangle, etc. Ordinate or perpendicular to member will be intensity of load, as shown. See, here, I showed randomly here. See, some will tell, sir, why it is going this way? Randomly. See, distributed load. This way it goes. This is the loaded length L naught. Now, see, L naught. These are the loaded length along the height. See, at any point x, I don't know. See here, you can see here, intensity is varying. Therefore, at any point x, I take a random point. At intensity of distributed load, at any point x is W suffix x. It is not W into x, W suffix x per unit length. I will explain this one. So, here directly magnitude, here intensity, that is the load per unit length. This is loaded length L naught. Now further, these all will come one by one now. Distributed load. See, class, something I am telling now. There are so many types of distributed load. One, uniformly distributed load. One. Second one, uniformly varying load. Uniformly distributed load we call UDL, short form, UDL. Uniformly varying load, you usually write easy language UVL. Also, see, not over. Also, distributed load can be irregular shape. See, it can be irregular shape, or it can be parabolic variation. It can be parabolic variation of third degree, or it can be trigonometric variation. Some people call sinusoidal loading, either based on sine trigonometric function, based on sine or cos. Sometime in the question paper you can see w at x equal to w naught sine 3 pi x by l, etc., etc. These are all there. But from our subject point of view, that all comes in some competitive examination or gate examination. Usual ordinary exam, it will not come. Academically, it will not come. And I should limit myself to subject requirement. So subject point of view, those are all not covered here. They are special cases. When the time comes, when requirement is there, I will explain at that time. Right now, from today onwards, for our course, distributed load means either uniformly distributed load or uniformly varying load. See, uniformly distributed throughout the length, uniform intensity. Uniformly varying load. Along the loaded length, it varies. How varies? Not this way varies. Uniformly varies. Uniformly varying means it is, remember, linear variation. Linear variation of intensity. It is linear variation of intensity, remember. Now, intensity of load varies uniformly along loaded length. Here, UDL means intensity of load is constant throughout the loaded length. See, if it is constant throughout the length, I just now told loaded length is L naught. Ordinate is intensity. If intensity is constant, everywhere constant, so UDL is represented by a rectangle. This is the representation for UDL. Close arrow marks show intensity. But everybody knows it. This is the correct way of representing UDL. Remember, the perfect way of representing UDL is like this. See, if it's a UDL, the correct way is to represent like this always. Don't count number of arrow marks. This way. But this will take some time. So to save the time throughout the world, what people do is, see, this everybody knows. This is the way UDL is represented. Then they will write intensity here, how much. See, this is or right here, very popular throughout the world. But even now, some standard textbooks, they write this way only. They maintain standard. See, they will tell what is this one. I will write the correct one. But time counts. So this is UDL. Uniformly varying load is represented by, I told, only linear variation for us. Parabolic of third degree, or irregular variation, or variation based on trigonometric functions. We are not bothered here. So here, uniformly varying load, UVL, is represented by either a triangle or a trapezium. Here, by a triangle, this way. Here, loaded length, intensity varies. I will give all the cases. Or it can be like this also. This also triangle only, L naught. Or it can be this way. Here, see, 0 maximum. 0 maximum, once again 0. Here, minimum to maximum. It can be reverse also. Don't by heart. Left side 0, right side maximum. No. And here, left side minimum, right side maximum. It is not that way. One side, one end 0, other end maximum. One end 0 reaches maximum, again reduces to 0. Any one end minimum linearly either increases or decreases to maximum. Or from that side you can tell, okay, here, this way linearly increases. That way linearly decreases. This is for uniformly varying load. These all you should take a snapshot and then write in a neat format, in a drawing sheet. And second round is there now, that also equally important. All those, or I told in yesterday's class, if you find difficulty for all these one, you should go for the notes. I talked about it a little earlier today. So therefore, I do not want to talk that way. because people will tell he is going for publicity for the notes. No. But I told the facts in the just now uploaded class. You go through it. There I told. So now this much is important. I will remove this one and go to next part. Continue. Just a recap. Concentrated load or point load. I already told directly defined by magnitude. So this W is magnitude of the load. Magnitude of load. Now, one important information. So many places what they tell is, I have seen it, it is utter nonsense. They will tell a simply supported beam of span L meter loaded by a point load W kilonewton, or simply supported beam of span L meter loaded by UDL of W kilonewton per meter. I strongly object to them. I will tell them, why you bought kilonewton and meter? What? Does it mean that what you are going to tell now is valid only for load in kilonewton, distance in meter? They will tell, no, you can for anything. Then why you told kilonewton? Why you told kilonewton per meter? So many reputed authors also do the mistake. Sorry, it's a wrong concept. I never write unit when I solve and when I go for bookwork type questions. See, for example, area of a rectangle, simple language, or area of a triangle. They will tell B be the base in millimeter, H be the height in millimeter. They will tell area equal to half into base into height, that much millimeter square. What is this nonsense? Are you teaching that way? For a person, you are forcing him to consider base in millimeter, height in millimeter. Why? Where is the rule? First of all, you simply tell, consider a triangle of base B, height H, unit, any unit of your choice, either millimeter or centimeter or kilometer or FPS unit, mile, furlong, anything. Here, load, why kilonewton? It can be Newton, meganewton, kilonewton or kilogram or gram, microgram, milligram. So what? You don't use units for bookwork type. I am dead against it. I will tell them, do not use that millimeter kilonewton. You tell general format. Okay, leave it now. It is for them. If they still do the same mistake, what I can do? It is not wrong, but that is not the correct way of explaining things. Okay, now, but when you go to numerical part, then you require kilonewton per meter, Newton per minute, correct? Then you require it. Okay. Now, remember, before going here, our purpose of this class is for different types of loads. You should write it. What we need is magnitude of the load. Direction is crystal clear. Line of action of the load, and also point of application. Sometimes along the line of action, if you change point of application, it will give complete nonsense results. See engineering mechanics, I told it there earlier. If you by chance shift a force to some other point along line of action, what nonsense result will come? So magnitude, direction, line of action, and also point of application, and most important, and also you should know how to find moment about any required point. These are all we are covering in this type of loads. When I take point load, UDL or UVL, either represented by triangle or trapezium, what I will tell, I will give example for you. How to find magnitude, 1. How to decide direction, 2. Where is the line of action, 3. And where is the point of application, 4. And then I will tell how to find moment about any point, some point there, some point there, wherever required. How to find moment? That's why this class is going to be in parts. One for point load, one for UDL, one for UVL with the triangle, maybe two class for UVL with the triangle, one class for load with the trapezium. Everything if you master, you will have no difficulty in future. Okay, now this I will remove. See, now make a note here. But before you leave this one and tell goodbye to point load, magnitude directly W. Okay, thank you. Over. Now come to, okay, this I will remove now, not required. Come to distributed load. In general, see, as shown random here. This is the loaded length. I am not marked here. If you want, write there. If you want, write. No space to write here. Okay, no, there is no space to write. This is X. X, okay, I will mark here. This is your loaded length L0. L0, okay. Now, in general, this can be either for UDL, see, it can be for UDL or UVL. In UVL, it can be represented by a triangle or trapezium, okay. What we want is, see, I will tell you what we want now. We want right now, that is in today's class, we want magnitude of total load considering loaded length L0. Today, that point of direction already clear. Where it is passing, that you will be knowing, it will be through centroid of the load diagram. That all we will discuss later. Today's class, we want how to find magnitude. See here, intensity, I told you, this is loaded length. You should write vertically, you are plotting what? This way you are plotting intensity of load. Intensity. So intensity varies. See, I have taken random. It is not for, it can be used for UDL, UVL. This is for anything. UVL or any variation, any type of variation. Even, see, even what? Parabolic variation. Parabolic of either second degree or third degree, or trigonometric variation, anything. Trigonometric variation, anything. So this is a general statement. Now, what you do is, you take a point X here along the loaded length. You should write it. Consider a point X along loaded length, and where intensity is W suffix X. W stands for small w. See, this all I will tell tomorrow, sorry, next class. Capital W for point load I told. Small w is for intensity. W intensity at the point X, that is Wx is per unit length. For 1 unit length. Now, write one more statement. Consider elemental length of load. Elemental length of load. So say dx length. You consider a small length dx of the load. Elemental means very small. Okay, now write statement here. Since dx is very small, you can tell intensity is constant for this loaded length. Therefore, the total load, or I can write here, therefore magnitude of load considering elemental length dx equal to, now common term, see, W is the load per unit length. We are considering length dx equal to your W suffix x into dx. This is a load. Like, very simple. How much is per unit length into loaded length? Loaded length is dx. For example, you pay 100 rupees for 1 meter length of a cloth. You want to buy half meter length, 100 into half, 0.5. You want a 3 meter length of the cloth, 100 into 3, that way. Okay. W into dx. This is for elemental length. So now I will write, therefore, magnitude, see, very important, therefore, magnitude of total load considering entire loaded length. This all you have to write if you want to understand. Entire loaded length equal to, there is a principle actually. So this I will remove now. This also I will remove. No, this also I will remove, not required. So magnitude of the total load equal to, see, when you know for elemental length dx, if a total, it is integration of what? W suffix x into dx. See, you write here, W suffix x, capital X. W suffix x is the intensity for a small length. Into dx will give load for elemental length. You want full load, integration. This is a principle. See, use this principle for which one? Either parabolic or second degree or third degree, or load represented by what? Some trigonometric function. In gate all you require trigonometric function like W equal to, they will tell intensity equal to 25 into sine pi x by something, kilonewton per meter, etc. Use this one. Okay, now, but we will not do this way. Okay, now see, correctly. Now, correctly see what is this one, right here. Open your eyes, open the eyes, and tell me what is Wx into dx. Someone, oh sir, it is Wx is this ordinate into dx is area of load diagram, okay, or area of diagram representing the load for elemental length dx. For elemental length dx. Okay, correct. That is this area. Now, what is integration of the area? Oh, they will tell, therefore, integration of W suffix x into dx is area of entire load diagram, entire load diagram for whatever length you consider. Oh, you can write here. Oh, therefore, what you can do in future is, instead of struggling like this, see, I remove this one now, this is not required. Therefore, in future, see, therefore, I write here, now onwards, for distributed load, any distributed load, magnitude of total load equal to area of diagram representing the load for loaded length considered. Very important. Loaded length considered. That's very, very important. I will tell you why important little later. You write here. Why he used the word loaded length considered, I will explain little later when the time comes. So right now, believe me, loaded length considered. Okay, now I will give you or there is one more option is there. I will tell you one more option, but we are not using it. Other option is, see, this is the most popular option. We will always use this one right here. We will use this now onwards. Other option is but we are not using it. You can use it also. Magnitude of total load equal to, remember, average or mean. Some people call average, some people call mean. Average intensity into loaded length. This we use for UDL later. Average intensity into loaded length. This also you can use. How to find average intensity? Make a note here. How you find average intensity? If it is linear variation, if it is constant, UDL, there is no average. Everywhere constant. Leave it. If UDL, there is no average. Everywhere constant. If it is UVL, represented by a triangle or trapezium, average is linear average. Maximum plus minimum divided by 2. Okay, over. But if it is a parabolic variation or other trigonometric variation, then average you have to get by integration principle. Okay. Remember, but we will use this only for UDL. Both are same. I will tell you next class you can make out. I will tell once again. UDL, we will use this one. But for UVL, we will go for area. When I start UDL, UVL, I will put big letters here. Everything big letters. Okay. Now, I will conclude the class now because introduction part is over. But before concluding, I will give an example for you. Just so that example becomes always, if I give an example, it will become crystal clear then. See, such examples, plenty I will give. Where means, in engineering mechanics or strength of materials and structural analysis, not much examples. In engineering mechanics, almost nothing. Strength of materials, yes, it will come. Occasionally it will come. But in RCC or steel, it will keep on coming. My students, they like my class, or actually I am very popular, you can tell, for such examples. So many people will tell now. Those who are almost about to retire now, old students, they will tell, sir, your examples you used to give, not structural example, usually money matter or some other example. Sir, that helped us a lot, sir. Lot of doubts are cleared. Okay, I'll give an example for you. For example, imagine, see correctly, just you write, imagine you are going by taxi. Okay. Now, what is the cost of taxi? See, somewhere here, when you started the journey, sometime 8 a.m. you booked a taxi, 8 a.m. It is 8 a.m. What happened is, at that time, the rate is, for example, 40 rupees per kilometer. There is a rule that taxi rate will not be constant. It will uniformly vary, linearly vary. 8 a.m. lesser or okay. So 6 a.m. I will take 6 a.m. 6 a.m. This I will put here. 6 a.m. It is 40 rupees per kilometer. This is equivalent to your intensity. How much is the cost per unit length, kilometer? Now, you took a taxi at 6, okay, right here, 6 a.m. you took the taxi. Then you traveled up to ಒಂದು 10 hours. 10 hours is 6 a.m. is 4 p.m. Correct? 6 a.m. to 4 p.m. is 10 hours. You traveled for 10 hours. You took the taxi for 10 hours. Correct, Vanisha? 6 a.m. not 4 p.m. 2 p.m. Okay, 2 p.m. Morning 6 a.m. you took the taxi. 6 a.m. up to 12 noon, 6 hours. Another 2 hours. How much total? No. 6 plus 4, 10, 4, correct. Okay. This is not structures. 4 p.m. So morning 6 a.m. you booked a taxi and started your journey, and 4 p.m. you stopped your journey. Taxi driver already told you, sir, our cost is, sir, linearly increases. How much? Sir, 6 a.m. our rate is 40 rupees per kilometer. Whereas at 4 p.m. it is 40 rupees. 40 rupees is too high actually. Luxury taxi. Imagine. Very, very luxury taxi. Okay. Sir, sorry sir. The cost is some 40, 60 rupees. It is 60 rupees per kilometer. Sir, our cost is that way, sir, computerized. 6 a.m. rate is 40 rupees per kilometer. But as the time goes by, computerized, at 4 p.m. it is 60 rupees per kilometer. And they will told, sir, linear variation. See, linear variation. It is linearly varying. Now, how to find total money to be paid? Total money you have to pay. Money you have to pay. You have to pay, that is equivalent to your magnitude of total load. Magnitude of total load. Total load. Only. Simplest way is, I write here, simplest way. Simplest way. One nimisha. The ink stopped there. I have to refill the ink. Otherwise, the shining effect is not there. Just I will tell you, simplest way is total money to be paid is total money to be paid by you is average rate into distance traveled. Distance traveled. Sorry, not distance traveled. Sorry. Average rate into what? Not distance. What is 10 kilometer? Oh, sorry, I told 10 hours here. Okay, distance traveled is, imagine, I should write distance traveled. From 6 a.m. to 4 p.m., imagine 10 hours are there. You traveled for, say, for example, how much kilometer? 25 kilometer. Okay. City driving. 25 kilometers is too small actually. Okay, I'll make one thing. 100 kilometer, some 100 kilometer you traveled. You traveled for 100 kilometer. Okay, now I require kilometer here. This is time. See, so 6 a.m. rate is 40 rupees per kilometer. At 4 p.m. rate is 60 rupees per kilometer. Therefore, average rate means how much is the average rate in rupees per kilometer into distance traveled. Otherwise, you put rupees per hour here, then okay. Distance traveled. See, it is linear variation. So, average rate equal to 40 plus 60 divided by 2. That everybody will tell the answer. Today, this rate is 40, that rate is 60. Add it, divide by 250 into 100 equal to 150 is 5,000 rupees. You have to pay 5,000 rupees. This is the easiest way. Or, do one thing. Or, imagine you are going for mathematical format. Do one thing. Right here. Consider elemental length dx. Elemental length dx here. At x from here. x from here, elemental length dx, where intense rate is r at x. R is the rate at x. Now 40 here, 60 here, this is 100 kilometer, this is x. So calculate what is r at x. At any, after x kilometers, what is the rate? Okay, how to get it? It is, see, now you have to go for linear interpolation. How? That I will not explain here. A separate class will be taken later for linear interpolation. I will write using my knowledge. 40 plus 60 minus 40 divided by 100 into x is the ordinate. Or y means, don't ask me, it is 40 plus 20 by 100 is 0.2. 0.2 times x. 0.2 correct? 60 minus 100. This is the rate in rupees per kilometer at any point x here. Now do one thing. Therefore, total money to be paid is, these are all I am telling only for understanding purpose. Those who are not interested can leave it. Total money to be paid is, this is the money to be paid, see, rate into x. First one thing, therefore, money to be paid for that elemental length equal to whatever is the rate, how much? 40 plus 0.2 into x is the rate per kilometer into distance is dx. Okay. Now total money to be paid is integration of whatever you got, 40 plus 0.2 times x dx. Limit is, x is from here 0 to 100. See, if it is not clear, this is a total money in rupees will come. This only for example, don't take seriously. I will integrate now. First of all, I should not integrate. I should write the answer, how much? 5,000 rupees. Let me see coming or not. How much? 40, integrate it. 40 into 100 plus 0.2 into 100 square divided by 2. 5,000 rupees, correct. Perfectly correct. Now, or I will rub this one now, close the class now by telling one more point. See, or as per the principle told right here, as per principle told just now, total money is also equal to area, right? Area of the diagram representing your journey equal to, see, this is a trapezium. Tomorrow or day after tomorrow, or next class or other class, I will give formula for area of a rectangle also I will tell you. Some will be laughing, rectangle area is telling, okay, triangle and trapezium. There I will tell you, area of trapezium is sum of the two parallel sides, 40 plus 60, divided by 2, standard 2, divided by 2 into distance between the two parallel sides into 100. Remember, I will write here, I don't know symbol. If there is a trapezium of, see, suppose this side is h1, this side is h2, this base length is a b, I will tell you, I don't know symbol tomorrow, area equal to sum of the two parallel sides h1 plus h2 divided by 2 into b. So 40 plus 60 divided by 2 into 100. Don't waste time calculating. It will come 40 plus 60, how much? 50. 50 by 2 is 40 plus 60. Yes, 40 plus 60 divided by 2 into 100. 50. It is 5,000 rupees. So you can calculate by 3 options. One of the option, average intensity into what? Loaded length. Second option, area of the load diagram. That is what we are using in future. Last one, by integration. Okay, now I'll wind up this class now. This is only introduction. Now systematically from tomorrow, I told speed also. Today I am not gone very slow because these are all introduction part. When I tell tomorrow how I will talk, I will tell this way. 40 rupees I should not tell. See, I will talk uniformly varying load. Let L naught be loaded length. Let W be the intensity of load. That way I will talk. Speed you can change if you want. Okay. Thank you. We'll meet in the next class.